Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Okay, class. Before we proceed to single phase full wave rectifier bridge rectifier with RL source load. Okay, we do a quick revision. Okay, in the previous class, we already discussed on the full wave bridge rectifier circuit. Okay, based on the waveform here, okay, voltage and current waveform, okay, we can prove that this full bridge rectifier can rectify from AC source to DC output. Okay, as you can see, the first waveform is the sinusoidal input voltage, whereby for this waveform we have both part, which is positive part from 0 until pi, and then negative part from pi until 2 pi. This is considered AC signal. And then the next waveform here is the output across the load. Here, okay, we can see the output waveform from 0 until 2 pi, or for the entire period here, okay, only positive. Therefore, we can prove that the output voltage here is in DC signal. Okay, hopefully you already understand how the full bridge rectifier can function as a converter, to convert energy from AC signal to DC signal. Okay, this is another type of full wave rectifier whereby we use a center tap transformer to provide isolation between the input side and the load side. Okay, please remember the dot convention here. These dots are placed on the top of the primary and the secondary windings terminal to indicate the current direction. Okay, if the dot is placed on top of the primary winding, it indicates that the current going into the primary winding. Meanwhile, if the dot here is placed on top of secondary winding, it indicates that the current direction is going out, okay, from the secondary winding. Alright, we also have discussed on the voltage and current waveforms. Okay, similarly, the first waveform here is the input source voltage. Okay, and then the second waveform here is the output voltage across the resistor load. Alright, and then the third and fourth waveform here is the voltage waveform for both diode here, D1 and D2. Okay, please remember, if we compare with the full wave rectifier R load, okay, all the voltage waveform and current waveform here are same except for the peak inverse voltage. I repeat, peak inverse voltage is the voltage across the diode during turn off. It shows that the maximum voltage across a reverse bias diode is twice the peak value of the load voltage. We also have discussed the voltage across a resistive load equation for the bridge rectifier of figure 4.1 here is expressed as equation 4.1. There are two parts of the equation here. The first part is when the supply voltage is from 0 until pi. Okay, we have the output Vm sin omega t. And then for the next half cycle from pi until 2 pi, we have the equation for the output voltage is minus Vm sin omega t. Okay, and then based on the instantaneous output voltage equation, we also learn on how to derive the average output voltage equation. okay, as stated in equation 4.2 here. And then based on the derivation of DC output voltage, okay, we further analyze to derive the RMS output current. Okay, we also have discussed the bridge rectifier with an RL load. Okay, and then for this one, you have to remember when the load omega L, which is inductor, when omega L is much greater than R, the output current and also the diode current here appears to be nearly constant. Okay, this is the equation for the instantaneous output voltage of the full wave rectifier with RL load. Okay, that consists of a DC term, which is V out, and also the even harmonics, the summation from harmonic number from the lowest one until infinity, and then Vn cos n omega t plus pi. Alright, the DC term here is equal to 2Vm over pi, and then this is the formula to calculate the voltage harmonic number. Okay, today we continue with a single phase full wave rectifier with RL source load. Based on the schematic shown in figure 4.5, you can see that this is another general industrial load that can be modeled as a series resistance, inductance, and a DC source voltage. Okay, there are two possible modes of operation for this circuit. Okay, the continuous current mode and the discontinuous current mode. In the continuous current mode, the load current here is always positive for steady state operation. Okay, meanwhile, for the discontinuous load current is characterized by current returning to zero during every period. For continuous current operation, one pair of diode is always conducting and the voltage across the load is a full wave rectified sine signal. Okay, based on this schematic, alright, the diode only turn on if the source supply voltage is greater than the VDC. Vice versa, if the source voltage is less than VDC, the diode will turn off. Okay, this is the average output current equation, okay, whereby we can calculate the output current here. Okay, the DC output current equal to V out minus VDC divided by R. And then for the discontinuous current is analyzed like the half wave rectifier of section 3.5. Okay, for example 9. Okay, based on the schematic given here, alright, for the full wave bridge rectifier circuit, the AC source is 120 VRMS at 60 Hz. Okay, the components value are given: resistor 2 ohm, inductor 10 millihenry, and VDC equal to 80 volt. Assume the current is continuous. We are required to determine the power absorbed by the DC voltage source and the power absorbed by the load resistor. So for this example, we need to calculate, first thing is PDC. The formula is given here. And then second one, we have to calculate the power absorbed by the load resistor, which is PR equal to IRMS squared multiplied with R. Okay, let's discuss the solution. Alright, for continuous current, the voltage across the load is a full wave rectified sine wave which has the Fourier series given by equation 4.4. Equation 4.7 is used to compute the average current, which is used to compute power absorbed by the DC source. Alright, before we calculate the PDC here, we need to calculate the I out. Alright, based on the formula given, okay, I out equal to 2Vm over pi minus VDC divided by R. We just substitute all the values given into this equation. Then we have the answer 14 ampere for the average output current. Okay, next we can calculate the VDC. Okay, equal to I out multiply with VDC equal to 14 times 80. So you have the answer here, 1120 watt. Okay, next we need to calculate the power absorbed by the resistor. Okay, this is the formula, but then we have to calculate first what is the value for the RMS output current. Okay, the first few terms of the Fourier series using equation 4.4 and 4.5 are shown in table 4.1. So that's mean we have to calculate all the Vn, Zn and In for the respective harmonic number here. Okay, start from n equal to 0, 2 and 4. So we have to substitute this n number into equation 4.4 and 4.5. Then you have the values for Vn, Zn and In. But please remember, the In is basically the peak current. Therefore, we have to convert to RMS value in order to solve the RMS current. Okay, 14 is the DC component when n equal to 0. Okay, this is basically the total DC output current. Okay, and then this one is when n equal to 2, which is I2. Alright, and then this one is for I4. Then so the answer here is 15.46 ampere. Okay, when we compare these two currents, okay, the first one is the average DC output current. Okay, just imagine when you are measuring the circuit currents by using multimeter. When you set the multimeter to DC, so you will have this value. Okay, if you set the multimeter to AC, then you will have the RMS value 15.46 ampere.